I don't know about you, but I often wonder how my calculator calculates certain things and figures things out. So one of the things that I'm always curious about is how does it continue to get closer and closer to the square root of 5? I mean, or an irrational number. We know these numbers do not terminate, they do not repeat. So how do they get them? How do they actually find what those numbers are accurately if we don't have an exact answer? Well, one of the ways that they can do this is using Newton's method. Newton's method is actually, you can write a program if you understand what Newton's method is. So, sorry for the blurry picture. We're going to go ahead and write over it, but this is the curve that we're talking about. So that would be whatever function we're talking about. And I want to know what the zero is. So I'm going to look for, using Newton's method, I'm going to look at some different things here. For instance, I'm just going to say that this is x1. So then this height would be f of x1. So this point right here would be the point x1, comma, f of x1. All right, and then basically what I'm going to do is I'm going to go up to that point and I'm going to draw the tangent line, which the tangent line may not go through this 0 that I'm trying to find right here. And as you see, it doesn't. It hits the x-axis at some other point. We'll call point x2. And we could repeat this process. So now I could go up here and I could draw the tangent line through there. And if you notice, I'm getting closer and closer to this 0 value here. So then I could go up and do it again. And eventually I will get close enough that it's almost 100% accurate. So here's Newton's method's formula. And you're going to say, well, how do we get that? What is that? It's actually fairly simple to derive. So we're going to deal with this point right here again. Remember that that was the point x1, comma, f of x1, and that it had a slope at that point. The slope would be for the tangent line f prime of x1. So now if I just go ahead and use my generic point slope formula, I'm going to come over here to do that. If I use my generic point slope formula, I would have y minus the y value, f of x1, equal to the slope times x minus the x value. So that's just our regular point slope formula. Now, what is the y value at every single one of these points as we go along? So what's the y value here, here, and here as we're getting there? Hopefully you notice that the y value would be 0 in all of those. So I'm going to go ahead and replace the y with a 0. And rewrite that. Now, I want to go ahead and solve this for the next x, or solve it for x. I want to know what that next x would look like, or the x I'm looking for. So I'm going to go ahead and get this x right here by itself. First thing I want to do is divide by f prime of x, 1. And then it looks like I would just need to add x1 to both sides. So I would have x1 minus f of x1 over f prime of x1. And if you notice, that's exactly what that is, only I have 1s instead of n's. So in other words, to get the next x value, to approximate this next x value, that was x2, then this would be x3 and x4, and we're trying to get closer and closer and closer until we reach a really good approximation that's almost spot on for that 0. All right, so you guys use polysymult a lot on your calculators. This is one of those things that polysymult is doing to find these zeros. All right, so on your calculator, you can just plug in square root of 5, and it's going to give you an approximation for that. And if you did that, you're going to get 2.2360679, blah, blah, blah. Okay, but what happens if you're writing the program for the calculator, or if you're writing this program for a computer program that you're developing, you're the next Wolfram Alpha, you're going to want to know how this works and how to write the program. So the first thing we need to do is we need an equation. This doesn't work if we don't have an equation. It doesn't work with just an expression. So if I just say that the square root of 5 is equal to x, I now have an equation. I don't like the square root of 5 being equal to x, so I'm going to go ahead and square both sides to get 5 equals x squared. All right, and our goal is to find the zeros, so I'm going to go ahead and set that thing equal to 0 by moving the 5 over to the other side, subtracting it. All right, now that I have my function, this is the function that I'm trying to find the 0 for. Now that I have my function, I'm going to go ahead and I'm going to pick an x. Well, maybe we should write the formula first. So let's write the formula. To find the next x value on the graph from xn, I need to take xn squared minus 5 over the derivative of this, and the derivative would be 2x. So then it'd be 2x sub n. So that's my generic formula. That's what I'm going to use every single time. So now I just need a starting value. Well, I know the square root of 5 has to be close to 2. I mean, we know it's between 2 and 3, but it's closer to 2. So I'm going to go ahead and use xn, or x1, I'm going to say is 2. So that would mean that my x2 is going to be 2, because x1, minus 2 squared minus 5 over 2 times 2. So I just plugged a 2 in for all the xn's. When I do that, I get 2.25. Not too shabby. And that's fairly close there, but not close enough. So I'm going to go ahead and repeat this process, but this is my new xn. So I'm going to plug that in to get x3. I'm going to plug that in as 2.25 minus 2.25 squared minus 5 over 2 times 2.25. And when I do that, I get 2.2361, getting even closer. All right, I had to do this all the way to 5, so I had to do it 2 more times, but once I got to my x sub 5, I found my answer, and if you guys want to go ahead and try it to verify, I found that I got pretty dang close. The only thing I was off by here was that 7. All right, so our first thing that we kind of want to do on all of these is find that generic formula that we're going to use to solve them. So this one is already set equal to 0. We don't have to do what we did on the last problem. It's already set equal to 0. So I know my x sub n plus 1 is going to equal x sub n minus, and then I'm just going to rewrite the formula, but I'm going to plug in an x sub n for all of them. So x sub n cubed minus 2x sub n minus 5. And that's all over the derivative. So I'm going to go over here really quick and show you the derivative. 3x squared minus 2. So I'm going to have 3x sub n squared minus 2. All right, so that's my generic formula. And then I just let the calculator do all the work for me. If we know that x1 equals 2, then x2 will be if we just plug 2 into each of these for xn's. So I have x2 will equal 2 minus 2 cubed minus 2 times 2 minus 5 all over 3 times 2 squared minus 2. And if you go ahead and grab your calculator and let it do it, you get 2.1. So that's x2. Now I'm going to plug that in to find x3. So I would have 2.1 minus 2.1 cubed minus 2 times 2.1 minus 5 all over 3 times 2.1 squared minus 2. And when I do that and let the calculator do that one for me, I get 2.094568812. So we're getting pretty close to that 0 there that the calculator would find for us if you just plugged it into polysimult. And again, yes, you have polysimult. Is it really necessary that you have to do this? No, not necessarily. But is it good for you to understand the program in your calculator? Yes, and especially because some of you might go into computer programming or engineering, and this will be vital. All right, I have one more example, and at this point you might want to go ahead and just pause the tape if this is the first time you're seeing this and you want to give this one a try and see what you come up with. Now on this one, notice that it is not written as an equation set equal to 0, so you're going to need to do that first. So I would say go ahead and pause the tape and then come back and we'll go through it. All right, so I noticed that this is the the 6th root of 2. If I set that equal to 6, if I set that equal to x, and then I go ahead and I take each of those to the power of 6, I get x to the 6th equals 2. Now if I solve that for 0, I get x to the 6th minus 2 equals 0. So this is my function. All right, so x sub n plus 1 is going to equal x sub n minus this guy x sub n to the 6th minus 2 over its derivative, and its derivative is going to be 6 x sub n to the 5th. All right, now again, I just plug this into the calculator. So when I plug, I had to figure out, what do I think x sub 1 should be? Well, I know the 6th root of 2 is very small. It's got to be somewhere around 1. I mean, it's got to be more than 1, or this would be less than 1, but it's got to be somewhere around 1. So I'm going to go ahead and say that x sub 1 equals 1. You have to have a starting point. And then I'm going to do my x sub 2 by replacing each of the x sub n's with 1. And when I do that, I get 1.16 repeating. Okay, this says find the answer correct to 8 decimal places. So I at least have to go one more, because right now 1.000 and 1.16 repeating are not to 8 decimal places identical. So I'm going to repeat this, and when I do this and I do x sub 3, I get 1.126444368. Okay, that's not to 8 decimal places sharing there. So I'm going to do it again, and I get 1.122499707. We're getting closer, and if you notice, this has, the first few are going to be the same. So let's do it again. And you'll find that you just have to repeat this method. And this is why you want to program this in a computer or in a calculator to do it for you. Let's see this one. We're getting closer. We finally have the first 3 or the first 4 the same. So we want to get to the first 8. So we have 1.122462205. Oh, look at that. These two are exactly the same as far out as I go, so even to the 9th spot. So therefore, this would be a decimal approximation. This is when your calculator would stop, because it's giving you the closest possible estimate, taking it out 8 decimal spots. And it's amazing how quickly, when you program it to do this, it'll do it in a split second, and you don't even know all of this is going on behind the scenes. All right, good luck on your homework. That's Newton's method.